Hey guys! Our project is about predicting NDVI values from globe land cover RGB measurements with multiple linear regression. So for some background context, mosquitoes are a formidable health concern. They are associated with numerous ecological factors, including temperature, precipitation, and vegetation. Our study will focus on that last factor, vegetation. Currently, to quantify vegetative density, researchers use a Terra Modis satellite to measure the Normalized Difference Vegetation Index, or NDVI, where 0 means zero vegetation and 1, high vegetation. But these measurements are often confounded by clouds, shadows, and landscape changes. So that's where citizen science comes in. People can make observations in their local areas, which can help scientists gain better insight of what the landscape is actually like, especially in areas where satellites cannot take accurate measurements. Thus, to help scientists gain a more accurate picture of vegetative cover, our project will connect citizen ground observations with satellite measurements.
So let's outline the goals for our research project. So through tools like the Globe Observer app, citizen scientists have become more involved in ecological research, conducting guided observations of mosquito presence and land cover features. In our study, we extract RGB, red, green, and blue quantities from globe land cover images to estimate NDVI. Our project not only numerically summarizes globe land cover images through the RGB values, but also explores connections between citizen ground images and satellite measurements.
Here's our approach. We first took land cover images from the GLOBE database, focusing on observations made by fellow 2020 SEES interns. From the GLOBE image URLs, we created an algorithm to fetch the image and calculate the median RGB values, which acted as our independent variables. Then, we used the Appears query database to get our dependent variable, NDVI measurements, for each GLOBE study site. We then combined RGB with NDVI values in a separate data frame. Using Scikit's machine learning packages, we conducted multiple linear regression analysis. Thus, we got a formula in the format predicted NDVI equals intercept plus the coefficients times the RGB variables, where R, G, and B each have a linear relationship with predicted NDVI.
And here are our results. We trained our model on a random sample of our dataset, where we got this formula to estimate NDVI. This formula makes sense given there's a positive relationship between the green values and the vegetation index. We then tested our model on the remaining points. This scatter plot shows the actual NDVI values against our predictions at the test locations. As you can see, our predictions are less spread out than the actual values. Our root mean squared error, which is the typical distance between our true and predicted NDVI, is less than our standard deviation of about 0.15. Thus, we can say our model performed reasonably well in predicting NDVI.
But what do these errors actually mean? Let's visualize this. So here's an example of a good prediction. In the image, we see fairly consistent vegetative ground cover without any majorly disruptive features like human development. Also, the camera is properly angled to capture a good summary of the area's land cover features. On the other hand, here's an example of a poor prediction. The photograph looks very green despite the small amount of vegetation. Our model sees green and assumes higher vegetation, while the satellite sees water and impervious surface and measures low vegetation.
To develop a more accurate predictive model, we can include other variables like image texture, vegetation types, and mosquito observations. We could also test other nonlinear mathematical models.
So now about the SEES experience. We appreciate the opportunity to learn so much from NASA mentors. We also loved collaborating with other students and scientists. Some challenges of SEES included collecting fieldwork and working virtually. But overall, it was an absolutely amazing experience from which we learned so much.
For me, SEES was a phenomenal experience that has helped me realize my love for scientific computing. In the future, I'd love to continue working with satellite data and create similarly predictive models.
For me, I realized how applicable machine learning was to literally everything and the importance of citizen science and ecological research, and I'd love to see more of that in the future.
I enjoyed having the opportunity to work on a scientific paper for the first time, and I also loved learning about the wide variety of possible careers in STEM.
Image citations?
Lastly, we would like to thank our project mentors, Rusty, Peter, and Cassie, for introducing us to in situ and satellite data collection techniques and for guiding us through the scientific process.
Thank you.
Thank you.